Hi everyone. As previously mentioned, I'm going to be doing a little tutorial today on how you can use LLVM to optimize your parallel programs. Helping me today is the wonderful George Stell, who this is going to be an interactive tutorial. So as you run into various things, he can help me try to figure out any installation or other related things. All the stuff that is in this talk is based off of, first of all, the original Tapir paper, which involves T.B. Shartle, myself, and Charles Lyserson, as well as some additional follow-up work between myself, George Stell, and Jihao Li. First step, though, which you guys should attempt to start to download in the background, because some of these things are quite large, is you should first pull the related Tapir Docker instance, and you should try to download the following Git repo. If it's helpful, a copy of these slides are actually inside of the Git repo, so if you get a little bit behind, or you want to look a little bit ahead, all of that's there. I'll give you guys a minute to try to find a partner if you don't have a laptop, download the various things, and then we'll start getting started. Yeah. OK. Everyone make their way to the various links, or at least got the links written down to start the download process? We good? I'm going to take that as a yes. OK, so as everyone gets set up, I'm going to give you a bit of an introduction. So first of all, building a parallel language, or generally a framework, can often be a difficult and often laborious task. But even so, once it is actually built, compilers and tools for such frameworks often create code that's far from optimal, and we'll be seeing this fairly shortly. This means users have to spend a lot more time writing code, and in fact, that code that they write ends up running not quite as fast. This talk will illustrate how support for parallelism inside of LLVM will both make parallel programs run faster and make it easier for languages to incorporate parallelism. In this specific tutorial, we're going to be using Tapir, which is an extension to LLVM developed by myself, T.B. Shartle, and Charles Lyserson at MIT that allows it to reason about parallel programs. For those of you who want to try it out more in depth later, the link to the GitHub repo is right there. And for those of you who want to see parallelism introduced into mainline LLVM, there's a BOF later today that you should come express your various feelings on. So the first tutorial that we're going to do is we're going to go inside and just basically verify that the installation is there. So we're going to go inside of Tapir tutorial/fib, and we're going to run make run. And in theory, we should be able to see something running in parallel. So I'm going to exit out of that, go here. It's clear. So previously downloaded the doc. Also, can everyone see that, or is the text too small? Let me see if I can make that ever larger. OK, there we go. So inside of the Tapir tutorial, we go inside of the fib folder. We look inside of it. I'm going to make clean really fast. And we have this fib.c file as well as the make file. Let's just go ahead and try to make it. I have some weird things with my Docker installation, so I actually need to sudo make it. And in theory, it should compile stuff for us. And we should be able to see now this LLVM file, as well as the corresponding object file. We can make run it. Again, because I have some weird Docker install things, I have to sudo make run it. And we can see it's nicely printing out Fibonacci numbers for us. If we were to open, say, htop or something, we can see, yes, it is indeed running in parallel. Moreover, there's a nice little extra check here at the top that tells you the number of workers that are actually running it. So let's take a little bit of a dive into what the code actually is. Here we just have some sample parallel code that, as you sort of probably guessed, just computes Fibonacci functions in parallel using a framework known as Cilk. Likewise, inside of the make file, and there's going to be similar make files in other parts of the tutorials, it'll make us an LLVM file. It'll make us an object file. It'll allow us to run it. We can also kill it. I'm just going to run the kill command manually. This one, I have it running for a very long time, explicitly for the sake of you can go in htop and make sure it is indeed running on all the various cores. Docker sometimes isn't necessarily happy about Control-Cs, so that's why the kill command is useful. You can see it inside of the make file, but I'm just going to also just do it manually here. And then it goes and ends the running of that. So yeah, specifically we have this Cilk code that'll compute the largest number of Fibonacci numbers, not necessarily the fastest algorithm, but hopefully in the background you're figuring out to see if this works on your computer or not. Likewise, we have all of the specific scripts that'll allow us to happily check that everything runs on our machine. Come on, computer. So now that we have all of this set up, we can try to do the fun parts of the tutorial. So first of all, I claim that compilers don't really understand parallel code. Whatever your favorite language is, if it's Cilk, OpenMP, X11, whatever it is, it doesn't really understand parallelism at a deeper level. So the first tutorial that we're going to do is we're going to try to make the fastest, eventually parallel, normalized code that we can. So to start, we have some rough serial code above, and inside of the folder Tapir tutorial/norm-mp, we have the full version of this code. So let's go inside of the Tapir tutorial folder and try to do make run. Let's see if this will. So run. So as we see, we have a really fast serial runtime just for, notice the actual runtime is the first number here, a number that tells you, rough normalization factors for the actual vector on the left to make sure it doesn't just optimize the entire thing away. So let's actually take a look again at what's going on inside of here. So we have two functions. We have the first function that goes through every element of the vector, sets the output to be equal to the input divided by the magnitude of it, and we have this wonderful secondary magnitude function that'll go through and compute the magnitude for us. Now, I have a 12-core machine here, right? So in theory, if I were to use all 12 cores and make this a parallel 4, I would expect a decently big speedup, or in theory, 12 times speedup if all goes well. So if we then look at normMP.c, I've done just that. I've used OpenMP this time as opposed to Cilk to implement a parallel version of the code to normalize a vector. So we've got the same thing. Let's try to run it. Let's see if it's run-mp or run-mp. There we go. And once again, it'll compile it and it'll run it. And if we take a look right here, we see that the time to actually run the parallel version is substantially worse than the time to run the serial version. But as everyone knows when they deal with parallelism, if you introduce parallelism, there might be some extra overhead to deal with setting up the threads, to do various sharing between various things. So perhaps this was just too small of a case, and we are spending too much time with that parallel overhead. So if we made the vector a lot larger, then perhaps we would get an actual speedup on top of this. So let's try to do that. So one key thing, if you look at this makefile in particular, and if you look at the run and the run-mp scripts, the last command there is actually the size of the vector. So just for ease, let's make it larger. Let's make it, factor of 10 larger. Let's see what that will do. And that won't be enough, but for the sake of testing, let's see what happens. So it takes longer as expected, but we didn't end up seeing a speed up. So let's add a couple more of these zeros here. Let's see what happens. Well, that doesn't seem like a good thing. Considering the first one ran in, like 0.1 seconds. I'm guessing this is going to be quite a bit longer. Actually, maybe I did it for slightly too long. Perhaps I'll remove one of these zeros. Try it again. Okay, I think I ran that for slightly too long. Whatever. It'll finish itself eventually. Anyways, point here is, in spite of running it in parallel, it was actually a lot slower. And in fact, in spite of the theory that we had initially that perhaps we actually needed a bigger vector to be able to see the speed up, this isn't actually what was necessary to see the speedup. So what happened here? Again, I can open up the code, and we'll see if any of you can guess exactly what was happening. Let me just make sure that that actually killed itself. Okay, CUDA container. Docker can sometimes be annoying. There we go. Anyways, so let's take a look at the code. So taking a look at this code and potentially the hint that's commented there, can anyone tell me what might have been going on, or any ideas what might be going on? And feel free to raise your hands. This is an interactive tutorial. It's ignoring the what, sorry? It's ignoring the attribute const. Sure, let's try to see what happens. Perhaps we'll add this print. Good idea. And we'll see exactly what's going on. I might make this a little smaller just for the sake of not having, theoretically, a lot of prints in case you're right. I'll make that a bit smaller. I should probably change that to Docker run script. I might need to make clean, but good, I don't need to make, yeah. So we can see here, prints out called mag quite a number of times. But maybe we were just unlocking the first case in the original norm example called mag a bunch of times. So let's introduce the same thing here, called mag. One of the best ways to verify your theories is to actually go and test it out, of course, in practice. Yes, indeed, for the serial version, we can see it only called magnitude once. So why exactly did this happen? So specifically, when we ran this on the serial code with O3, it was able to happily do everyone's favorite optimization, loop invariant code motion, noticing that it could move it outside. Now, this did not end up happening for the parallel code. And why is that the case? So if we take a deeper look at the actual LL file, and if you go and look at the LL file that was produced, we see something like this. And the body of the loop actually got outlined. So you can see this KMPC for call, and if we go more deeper into it, we can see that the magnitude function is still inside of there and being called multiple times. So if we take a deeper look at the LLVM compilation pipeline, we start again with C code usually. We have our front-end clang produce LLVM for us. We run it through our optimizer. We eventually take the codegen to create our executable file at the very end of the day. So what happens, say here for Cilk Plus, or OpenMP. In this particular instance, we have our OpenMP code. It is translated down to LLVM, and all the parallel language constructs are being made inside of LLVM itself. We run the optimizer on top of that, and finally we codegen and run it. So for a normalized example, I'm using, again, a modified version of Cilk here because the OpenMP version gets a bit more nasty with a bunch of extra runtime calls. But roughly what happens is it takes the body of the loop and makes a separate helper function with it, and it's passed to a runtime call that executes every iteration of the body of the loop. Now, if you take a look down there at the original norm, or in our case, it was called mag, it's a totally different function, and we can't even tell where it's being called or if it's called at all, because we don't know what's going on with that opaque runtime function. And thus, if it's confusing for us to look at, it's confusing for LLVM to look at, and it's not able to do the optimizations that we want. And if you remember that fib example we had at first, in reality, it's actually a lot more complicated with all the things that come out with set jumps and so on. And more generally, optimization passes end up struggling to optimize around these runtime calls. So this is where Tapir comes in. Tapir stands for Task-Based Asymmetric Parallel IR. Effectively, what we did is we extended LLVM to be able to represent the parallelism of any particular program. So now instead of having a front end that lowers down to these runtime calls directly, we can lower down to LLVM plus these taper instructions. We can optimize on top of these taper instructions, and then we can convert the taper instructions down to the runtime calls after the optimizations are done. Meaning we can take advantage of all the optimizations inside of LLVM across parallel control flow. So second tutorial is now we're going to look at how it works on actual taper code. So if we go into the side of the folder taper tutorials/norm, we can try to see this in action. So let's do that. So once again, we have a norm file and we have a make file. If we look at norm, just as an example, now it's written in Cilk, or we have two versions. We have one written in Cilk and we have one serial version. If we look at our make file for a sec, once again, we have a couple of nice objects here that'll let us do things, as well as the ability to look at the IR itself. So let's actually just look at the IR itself at first. So let's do make taper. Except because as previously mentioned, I have a weird Docker install. I need to fix that. So if we look at taper pre.ll, we can see what the IR looks like with taper inside of it. So we're going to ignore mag, we're going to ignore the serial version, we're just going to go straight down to the parallel version. So again, we have fully unoptimized IR, all of the alicas and so on, eventually going down. And we have this funny little instruction called a detach instruction. And then we have the body of our for loop, and we'll see our call to mag right here because it's just directly translating down into the taper sort of version. We have a reattach instruction, which we'll find out later denotes the end of our parallel task. And finally, we have a synchronize instruction, which we'll again learn later, denotes that our parallel for loop in this particular instance is over. And the first thing that you can sort of notice is it looks very similar to how the serial for loop, which if we scroll up, in fact, looks like, except now we have a couple of extra instructions, namely the detach, the reattach, and the sync. In other words, we don't have this boxed additional helper function that's come out of it yet. So now that we've done that, let's first of all open the make file again. So let's see if this will work. Let's make these various things fast and slow. So in particular, what I have here with fast and slow is the slow version tells the compiler to do all the optimizations, or specifically to lower taper immediately to the runtime calls, then perform all the optimizations. This is what typically will exist in the compiler, but just to double check that taper isn't doing anything wonky in the way that it lowers to runtime calls, or Cilk, the front end or runtime, isn't doing anything wonky. We want to double check that to keep it consistent. And then the fast version says, run all of the optimizations when you're in the taper phase, and thus, when you lower, in theory, it should be faster. So let's actually run it. Make run fast. And we have a decent sort of runtime there. And if we increase this again, we'll see the same sort of like runtimes that we'd expect. And if we do make it run slow, we can see there's a significant difference, first of all, between the parallel runtimes of the fast and slow version. But then also, if we actually increase this a bit, I'll be more conservative in case I increase it too large for this computer to run right now. But let's see. If you increase this sufficiently, if you increase this sufficiently, you'll be able to see the parallelism happening, and then also you start to get the advantages of the parallelism on the code. Mainly because right now it's too fast that the overhead of the parallelism in the smaller cases was dominating the runtime, but as you add more work for it to do, then there's enough work to counteract the fact that there's this additional overhead for parallelism itself. So, moving forward, again, we noticed that inside of the taper version, we have these 3 new instructions: detach, reattach, and sync. Overall, the source code looks something like this. Now, this is specifically for that original fib example. First of all, we have this sync region. This I'll come back to in a moment, but we start with the detach instruction. This denotes the start of a parallel task. This goes then to a separate part of the CFG where we have the things that we want to run in parallel with the rest of our tasks. Specifically, it must end with this reattach that has an edge going back to what's called the continuation, or the other tasks that we want to run simultaneously. Finally, we have a synchronization statement, which simply denotes that by this point, we want all of the tasks in our current region to have completed. And this is specifically why we have the region instruction right there. It denotes all tasks within this region synchronized together effectively. Yeah. Sure. In this particular instance, you specify the tasks as opposed to the number of threads. So if you wanted to have something run, say, for 10 separate threads, you would end up having 10 separate tasks, and you would hope that your runtime has sufficient threads to be able to schedule them all like that. The more details of how Tapir works is we assume that you have a scheduler that will then map the tasks to the specific runtime threads. Yes. Yeah, and I'll go a little bit more into how the backends work. In particular, right now we're running with the Cilk backend, though this one we could also run with, say, an OpenMP backend or PTEX or whatever else backend that you want. And the way that it gets scheduled is sort of free workers will pick up some of these particular tasks. If that makes sense. Cool. Likewise, if you want to represent a parallel loop, it looks almost identical to a regular serial loop, except now we have these detaches around the body to denote that every task inside of the loop can run independently. And of course, we have a sync at the end saying, once we get outside, at the end of the loop, we want all of the things in our loop to have completed. So let's go take a closer look at exactly what happened in this normalize example. So we're going to go inside of Tapir tutorial now, LLVM. So let's do exactly that. LLVM. CD LLVM. Make clean. So here, once again, we have two files. We have our make file and we have the norm, except now I've modified the norm slightly, so then we only have this particular part that we want to make reading it slightly easier. Moreover, if we take a look at the make file and see what's happening, what I'm going to do is first, I'm going to create a version of the LLVM with Tapir inside of it with no optimizations, and O0 creates opnone, so I just have this hack to get rid of the opnum. I run some initial optimizations like mem to reg and loop rotate, such that then we're looking at the point where we can do loop invariant code motion, and then now we can see what it looks like right before loop invariant code motion, and verify, hopefully, that loop invariant code motion is actually run on it. And make icm.ll, and in theory, it should go make all of these specific phases. So if we take a look really fast at so if we took a look at mem2reg.ll, which is after all of the optimizations that will then allow us to, in theory, do loop invariant code motion, we can see right here the call to the magnitude function, and then we have our for loop in a nice form that loop invariant code motion can go through. And then if we go to LLVM, happily, we see that the magnitude is now outside of the loop. We did it. We finally did the optimization. And it works as intended. So how does this work to allow the existing optimizations to actually run on it? Of course, we have the fact that it looks very reasonable to analyze, but this doesn't necessarily mean that all of the things will actually run nicely on it. So the secret sauce here, effectively, is that most parts of the compilers can apply standard assumptions on this modified CFG. And as a consequence, most of the optimizations can just work on it out of the box. And those that don't work on it in the way that expected, you can do a couple of minor tweaks on top of it to be able to have them apply nicely. So I'll give you an example. Namely, suppose we want to do common subexpression elimination. Suppose we have some fictitious parallel language on the bottom, and it translates roughly to the CFG on the top. I did some minor simplification just to make it easier to see. So specifically, we will notice both the div and the div2 compute the same expressions, though one is now computed inside of the task, and the other one is computed in the continuation. Now, in theory, we should be able to do an optimization where we don't compute the same work twice, but we compute it once before both of these things. And standard CFG just says if you have two expressions that are always computed, move them up to the top of that so you don't need to compute them twice. And It just perfectly works like that. Great. Another example where there were a minor modification needed was Tail-Recursion elimination, where specifically what we needed to do was to say, just for standard Tail-Recursion elimination, ignore the sinks before the recursive call, and specifically then add a sink again before the intermediate returns. And then this allows the same sort of thing where you have a break to the top to do the Tail-Recursion elimination, except we had to do this minor modification with sync on top of it. So then it'll run nicely on the parallel equivalent of the code. Now, of course, regular Tail-Recursion elimination works perfectly fine on serial code without this modification, but to get it to work as we would want it to work on the parallel code, we needed to do this minor modification. So overall, to things like dominator analysis, common expression elimination, and most other optimizations themselves, we had no change. And to other optimizations, such as loop invariant code motion and Tail-Recursion elimination, there was a very minor change to make sure that it was able to work as much as we wanted to. Again, these things were not necessary to have it run correctly on serial code or even correctly on the parallel code, but it made it run faster, which is something nice. In fact, we tested this on a wide array of benchmarks, both the sort of version that it compiled through Tapir with these optimizations, the version where it didn't. And here we are comparing the serial one-core sort of version with the parallel version with and without Tapir. And ideally, you would be able to have your parallel version run as fast as the serial version. Now, of course, in practice, this may not be true because you have things like the parallel overhead that we saw at the very start, or simply to be able to divide up the tasks necessarily requires some additional optimizations that can't be done. But we saw in practice, for like a third of codes, you were able to get roughly a third speed up on one core. And this actually ends up translating to a larger speed up on multiple cores. For some of these, we got a minor speed up, and we didn't really end up slowing anything else down, which is to be expected and what we sort of desired out of it. The next sort of stage in this is, OK, now we've managed to get all these serial optimizations on parallel code. So parallelism now really won't end up slowing us down from the compiler level alone, but we also want to make it run fast for other reasons. Namely, to ensure reasonable performance, a lot of these existing parallel frameworks end up implementing parallel-specific optimizations. So one example optimization that's commonly done in frameworks is what's known as coarsening. And in fact, OpenMP does this to a minor extent, and just to fully highlight it, I told OpenMP not to, if you look very carefully at that code. For instance, what's here is to overcome some of that overhead of running things in parallel, it'll strip mine the inside of the loop. And thus, instead of having the parallel overhead for every iteration, you have it, say, for every 1 in 4 iterations. And best case, you can, say, get a 4x speed up. A couple of other sample optimizations that are nice for the parallel case is existing code and parallel frameworks can leverage polyhedral optimizations and just generally scheduling optimizations such as loop fusion or tiling with relatively no extra effort. And this is particularly useful for the parallel case, where you have a lot of interesting things such as caches and whatnot to care about. And say if you wanted to have this eventually mapped to an accelerator, such as a GPU, you want to make sure that all of your loops are scheduled with the 3 parallel loops on the outside and the other pieces on the inside. And being able to actually analyze parallel code is very nice for being able to do that, because now we have a nice framework for representing the parallel code that goes in the first place. And again, in this particular example, best case, you can get, say, 2x or something like that. Another sort of minor example is, say, you can do something like task elimination, where you notice you have 2 separate tasks and then a sync. There's nothing running in the separate theoretical task after the original is attached. So instead of having an extra overhead wasted on calling Baz, then we can just call it directly. And it sounds somewhat trivial, actually, but it ends up being especially important for OpenMP tasks, where if you want to represent something like fib linguistically, you're required to always have this extra detached there. And thus, if you were to do this with or without the task elimination, you can end up with a substantial improvement, specifically if you're using the OpenMP task frameworks. Yeah. So in this particular instance right here, it's always beneficial to do so because there's no additional work after the last tasks. So there's always benefit to being able to do that particular merge. If you also have work afterwards, then this comes into the place where you would want to have a heuristic. And in this particular example, and I'll talk about this a little later, you have both a front-end language, and you also have a backend which actually executes it, say the OpenMP runtime or the Cilk runtime or your PTX runtime. And depending on which runtime you use, you might want a different heuristic to say if these things should be merged. So if you have really, really lightweight threads, you might not want to do as much merging because you have full advantage of the parallelism. But if your threads are slightly more heavyweight, then you would want a different heuristic for doing so. And there are ways to specify this. So the way that these parallel optimizations are implemented today is that every parallel framework is independent, requiring large amounts of code duplication, meaning my version of this coarsening requires you to have your own version of coarsening in all of these frameworks. Moreover, a lot of these low-level optimizations that we already rely in LLVM, such as that looping fair and code motion example, sometimes these frameworks try to make sure that they don't lose out on that. So they end up duplicating this code as well in the front end, which is not ideal. So generally, we have parallel pipelines that look something like this. Every framework has their own front end with their own optimizations. They go to LLVM with the respective runtime calls, and eventually it runs on the respective runtime, and that respective runtime alone. The nice thing is that Tapir allows one, and specifically parallelism inside of LLVM, allows one to represent and work with parallel programs, and using it as a common intermediate representation allows for various parallel backends and frontends, which first of all is cool because then you can compile code that's written, say, partially in Cilk, partially in OpenMP, partially in MPI or something like that, and compile it to a single version of this or to schedule whatever is optimal, combining them all together. And you have one set of common parallel optimizations that can be used by all. And moreover, if you have a tool that's only usable by one of these frameworks, you can in fact use this specific tool on all of the frameworks because you can compile to a version with that runtime and then use that tool if it's useful for debugging, for instance. So in an ideal setting, we have something like this, where we have all of the various parallel frontends go into the LLVM plus parallelism, some common parallel optimizations, then to the whatever backend you like. And we have a lot of these things previously implemented, some to full sort of specificity of the spec, and some of them partially to. And moreover, if you have your favorite parallel runtime or favorite parallel language, you can add your thing at the top or the bottom and then take advantage of all the things that currently exist. And moreover, being able to choose these parallel runtimes is kind of interesting because you can actually get, in particular instances, a faster version of the code if you use one runtime as opposed to another. For instance, in OpenMP tasks, they're not as optimized as Cilk tasks. So for things that are very dependent on the task overhead, such as Fibonacci, it ends up being such that the Cilk version is better. But for other pieces where you have less task-dependent pieces, but overall sort of like thread synchronization pieces, it can end up being the other way around. Moreover, either way, it's faster than the default clang lowering process because you can take advantage of, say, only passing in the variables you need in registers as opposed to having one struct that's passed in and having to do memory accesses on it. This is examples from the OpenMP benchmark suite. And in fact, some of these were really large, so I didn't make the full version of the graph, but if you're interested, that's the full version. So now the question is, how do we optimize your parallel code? So if you have your own front end, the way that it would look is you have your code. You would make a lowering sort of process that lowers it to Tapir. This is the same sort of place where you would have, say, your IR builder that built LLVM IR, except now, in addition to building the regular LLVM IR, you would also build these parallel instructions on top of it. And I'll give you an example of that. Likewise, if you have your own runtime that you want to test out, you would have a lowering pass implemented on the back end of Tapir, where you would lower from Tapir, sorry, that should say lower from Tapir, to your runtime calls, and then eventually do the code gen. So if you want to add a Tapir front end, the thing that you do is simply to add these detached CFGs wherever you'd have a task, and you would denote all the dependencies in your program using the synchronization instructions/regions. And as a sample, let's look at how this might look for a parallel loop in the halide code gen. So the difference from the regular serial loop is now we have this create detach on top of the IR using the IR builder. We also have a not shown, but we have a create reattach inside of the code gen. And finally, at the very end, we just add in a create sync. The rest of the actual code gen for creating the LLVM is almost the same, just we add a couple of instructions to denote the parallelism of the actual code. So let's talk about adding a Tapir backend. This is to say, how do we take code that is currently in Tapir and how do we run it on whatever backend or machine you have? And there's, in fact, 3 stages of this, of which you can choose whatever's most suited for what you're doing. We have a polyscope-based technique. This is ideal, say, for doing mappings to GPUs, we found. You can have a loop-based technique if you have a specific optimized primitive for handling loops. You can have it go directly to that. and we also have the task-based technique. And in fact, these things go in stages. So first, if you have a scope-based technique, it'll run and try to analyze and do all the lowering it can there. Then it'll run the loop-based technique. And for instance, if your loop-based technique created tasks, then the task-based technique will run after it. So then you can rely on the later task-based technique to be able to take that up. So how do we actually build a backend? And I do have an example of this if you want to try to compile LLVM on your own, but since I assume that's going to take a while, I'm just going to show you the code and how this actually works. So if we want to build a backend, we override this taper target, which denotes how to take the taper instructions from the external taper lowering process and create your specific runtime calls. And the specific parts that we're going to look at is we don't really need to implement the pieces we don't need. So for instance, it allows you to process a main function or any individual function or helper function that is running in parallel if you have specific structs that are necessary to set up runtime variables. But in this sample backend, I'm doing the easiest possible thing, and I'm going to assume we don't need to do that. Likewise, if we want to be able to do specific things that process loops, we can choose to do those. But again, in this particular backend, I'm choosing only to do a backend for tasks, as opposed to one that optimizes for loops specifically. OK, so let's look at, say, how one can end up lowering the detach. So the first thing that we do is we outline the task, as most of the runtimes that you'll end up doing require, say, a specific function pointer to the task to be able to run it. And in my sort of sample, my backend runtime, that's exactly what I'm assuming you do. Just for ease, we are going to ignore the previous taper task by removing all of the references to it actually running in the rest of the code. Then now we change the call to the extracted task to be called with our runtime, as opposed to being called directly. So now it'll actually end up running in parallel. Likewise, if we want to create a sync, I'm just going to assume that my runtime has a special sync function that'll go look up all of the threads in the current scope and then go remove it. And in this particular instance, I pass the function pointer to the outlying function, and I assume that this backend specific sync instruction will do all of the lifting behind it to make that true. And if you have something more complicated, of course, you would add the slightly more complicated things that whatever your backend would end up doing. Likewise, another useful thing here, which is done for the default loop processing in the case where you don't actually implement specific loop processing, is it'll ask for the number of workers to try to do a nice chunking of your parallel loops. And specifically, it asks for 8 times the number of workers. And in our simple backend, we have a runtime call that exists, get num workers, and we return that times 8, for instance. And that's it. If you want to implement a backend for your particular framework altogether, including the separate header function that's required, in this case, it's like 150 lines of code. Of course, if you have a more complicated backend with structures that need to be initialized and so on, then you're going to end up with a larger amount of code, but that's dependent on whatever backend that you want. Moreover, we can take advantage of all of the taper optimizations, and automatically, all of the languages that go down to taper, say Cilk, OpenMP, et cetera, you have valid programs or benchmarks for whatever your runtime is. So you don't need to worry about creating those, since we can take advantage of the fact that those exist from the other front ends and languages. And just as a test of running this actual out, we have a specific taper target flag saying, emit it now with my backend, and we can notice it does exactly what I expect. The previous detach is now replaced with this runtime call to my backend detach. Likewise, the sync is now replaced with this specific my backend sync, and so on. So the third and final tutorial during this talk is going to be talking about some of these shared tools that are useful, especially when you're creating both the front ends and back ends. So when you're creating things to handle parallel codes, a big issue that you might run into, for example, is whether or not you introduced erase by accident as the compiler writer. It's also possible, of course, that the programmer introduced erase, but it's especially bad if the compiler secretly inserts erase where there didn't exist one in the code. As an example, you might accidentally say, make a private variable public, and so on. So as the example, we're going to look at a race detector that exists for one particular backend, the Cilk backend. So let's do that. And just to sort of explore how it works, just make it clean for a sec here. And again, we have our favorite fib function from before, just acting all normally. This one doesn't have any races inside of it. We can also look at the second fib function, fibbug.c. Here I add this extra variable z, right? And I have a race on z every time that I call it, which is not ideal. And then I can, first of all, just make clean to double check. Make. It'll compile these things. The specific flag that already exists for this tool is called like the Cilk sanitizer, so you can do -f sanitize Cilk. If you wanted to build your own tool, you could, again, whatever ways you deal with your tool, and just set the backend to be the relevant backend for using that tool that you want to use. So let's see. Let's do make file, and wrong folder. cd san. So we're going to now just run the regular version. There we go. And we'll see, this time I had it do less times of running the actual Fibonacci function. It was able to say as a race detector there were 0 races detected, and that's great. That means that our code is race-free. We can also imagine doing make run bug. And as we can see, the race detector is yelling at us a lot because there's a number of races that are continuing to happen. And I should probably kill that. Or whatever, it isn't that much. Anyways, has still the final result out, but you can see, oh, look, you're having multiple writes to the same variable z, you're racing on top of it. So these sort of tools make it very easy to be able to debug your front end to your back end if you have a bug in these sort of places, as well as if your end users actually have a bug in their code, they can choose to use whatever tool is most convenient for them, not necessarily the tool that is available for that particular framework, which is something that's really nice. So the general takeaways from this talk is that with relatively little modification, the compiler can end up doing a lot of things to make your parallel programs run a lot faster. The first thing, which is from the original Tapir paper, is we can now run serial optimizations on parallel code. We can also now build and share parallel optimizations and parallel tools. And moreover, we can mix and match parallel runtimes. For this particular implementation of parallelism inside of LLVM, we have ongoing development, bug fixes, new optimizations, and so on. And it's available on GitHub. And once again, if you think that this is something that you would like to have in mainline LLVM, come to the BOF today, and we can have various talks on how we can get something like this inside of mainline LLVM. Yeah, any questions? Yeah.
Questions?
Thank you for your talk. And so I understand that you said that it didn't take much modification to support a special instruction, but my question is, why not using intrinsic?
Sure. So the specific reasons why some of the intrinsics didn't end up working initially. And it turns out if you come to the BOF, we found a way to do some of these built on top of intrinsics is because doing the analysis of the code and having the ability to have some of these pieces act as barriers and moreover have multiple successors was a lot easier to do in the first implementation of this with the terminator instructions rather than intrinsics. But in fact, if you come to the BOF today, you'll learn a little bit of how some of these things can be implemented with intrinsics, though there is a bit of a trade-off in terms of you can't do necessarily all the optimizations you want at first. Yeah, so.
Okay, so I got a follow question. So I remember one of the slides says that Tapir can be a common middle IR for multiple runtimes or parallel front end. But can you justify why your Tapir is better than other? Because for example, Halide is also an IR. Sure. And why you are saying you are better than other Halide?
Sure.
Yeah.
So it's not necessarily that Tapir, for instance, is better than Halide. Halide and Tapir have both different jobs that they do. Halide allows you to do optimization and scheduling at a higher level where you know all of this information. The thing that Tapir provides you is all of the nice optimizations and scheduling related pieces that exist inside of LLVM. And moreover, when you combine a lot of things together that aren't coming from your DSL that goes down to Halide, you still can get benefits of optimization on parallel code at the LLVM level. So neither is necessarily better than the other, and ideally you would have a system that's able to optimize at both levels. Specifically, Tapir fills in that gap where a lot of the optimizations inside of LLVM were not necessarily being able to be run on code that was being brought down to it, if that makes sense. Yeah.
More questions? Yeah.
So you mentioned that Tapir can be used for the OpenMP implementation. I was wondering in the Tapir how you're going to represent reductions, like array reduction, array section reduction in the Tapir.
Sure. So in this particular regard, there are two ways that you can imagine implementing. And I'll go slightly more generally than just a reduction. But suppose you have something that isn't a specific parallel task. One option you can always choose to do is you can use your existing runtime calls in addition to Tapir. So for instance, you had a runtime call that did a reduction. You can leave these pieces in, and that'll optimize all the parallel aspects, but it might not necessarily optimize the reductions out. Actually, a piece of work that we're looking on with specifically to reductions is to be able to have an additional way of saying reductions are these special tweaks on top of memory, and then you can use all of the special LLVM internals for doing optimizations on reductions. But the moral of the story is whatever your particular additive thing on top of the parallelism itself, you can always choose to implement that by passing those runtime calls directly through, and the parallelism itself will end up being optimized using a framework like this. And it turns out that most of the time you want to do optimizations, things like concurrency and other pieces end up getting in the way of that, and not just because there's, say, a runtime call, but because these pieces cannot be optimized because you're expecting certain behavior to come out of them. However, in specific examples, for instance, reductions, you can add a little bit on top of this and get a couple of additional optimizations through it, if that answers your question of how you would implement a thing like reduction in Tapir.
Yeah, I'm more interested in how the reduction semantics is building on the Tapir representation. That's my sort of my question. I know you are trying to think about how to optimize when you have a reduction code inside your Tapir or LLVM, right? So I was more thinking about how to preserve the reduction semantics when you do the optimization without breaking. How the Tapir going to embed those reduction, like I have a reduction plus with the array section there, how you're going to represent it in your IR.
Sure. So again, specifically the default way to represent it would to be having these additional runtime calls that would represent the reductions. We also have some work that is yet to be published that shows promising results for having sort of attributes on top of existing memory operations along with Tapir for being able to represent reductions effectively,
so
which I'd be happy to talk to at length offline.
Right. We have a different way. In the above, we'll talk about how to represent those stuff. And another thing is how you're going to represent task dependence.
Sure. And
because for OpenMP, we have a dependent clause, so you can specify the dependence between the tasks, right? So the Tapir, in the Tapir, how you're going to represent those dependencies between the tasks.
Sure. So my specific response to that is Tapir as a model represents nested parallelism. And that's specifically, I'll go to, where's, yeah, so specifically that's the case where you have parallel regions where each of these regions is able to synchronize all of the tasks inside of that region, and you can nest these things arbitrarily. The choice we made was specifically to do this as opposed to an individualized sync, because it turns out the frameworks that allow for an individualized sync cannot be optimized without breaking optimization for everything else, and moreover, these optimizations don't end up having a large differential on top of it. You can also imagine creating additions on top that specifically represent the individualized syncs as opposed to the nested sort of sync type pieces. But again, empirically, we found that these don't give the ability to do additional optimizations on top of it empirically. Though these can, of course, be added in, but just we didn't find a need necessarily for most cases. Yeah, if that.
More questions?
Well, thank you for doing this. That sounds very useful. I was wondering if you had planned for a TBB backend for Tapir.
Sure. Actually, at one point, there was a couple of Intel folks who came. I'm a graduate student at MIT, and we spoke with them a bit. And in theory, we can make a TBB backend. I tried to contact that individual because they're obviously more knowledgeable than TBB than I, and at the time that person was busy, so we didn't end up making it. But if you would like to help make a TBB backend, I'd be more than happy to like give you the Tapir-related knowledge, and we can make one if that's something you desire.
Yeah, maybe that might be an idea. As a secondary question, I was wondering if you had any scheme for like determining like the grain size, the appropriate time when you should switch from a parallel recursion to a sequential version because the overhead is too small, or is that just left as the runtime for an adaptive determination, or can you pass int from your domain-specific jitter to drive that decision through the LLVM IR?
Sure. So specifically, the way that we resolve this now is we have two ways of going about it. If you see this, for instance, the process loop, we have loop spawning hints. So you can, at a front-end level, add metadata on top of these parallel loops that specify specific things that you want, for instance, explicitly a grain size of 1. And then these should be abided by the backend. Secondarily to that, we have the ability to run heuristics to say, this is empirically better than this other thing because of how this backend works. And these are very backend specific. So these specific heuristic values end up being implemented by backends. There's also a couple of places where semantically one is strictly better than the other, which is that one case I had earlier where there was nothing being run in the second task. So this is strictly better. And the way you would end up getting the best performance is by doing a combination of these things. So you can, of course, manually specify it. You can have heuristics based off of the backend and the semantic places where semantically you can prove that it's strictly better.
Okay, thank you very much.
More questions?
There you go.
Maybe I have one last question.
Sure.
Do you think it would make sense to add something to represent data level parallelism as well? Because currently for CUDA, as far as I understand, you have to create, so if you have a kernel, you create task, and then you have to create multiple versions of this task per thread, right?
Sure. So specifically with respect to data parallelism, you can represent code that is then later going to be sent down to the CUDA level in something like Tapir. The reason we chose to go for the task-based parallelism is for two reasons. First of all, there's a lot of frameworks that we tended to use and saw that a lot of people used the task-based sort of model as opposed to the database model. And we figured out a nice way to be able to represent all of this in a way that could be optimized. There are some aspects of the data parallelism that can be represented here, but this is a place that we've yet to fully explore. And if you're particularly interested in that, you should feel free to talk to me about it. We can try to figure out how to make that work as best as possible.
Sure. Sounds good. Thank you very much.